Imagine looking up at the night sky and spotting not one, not two, but four suns blazing together in a cosmic dance. It sounds like something straight out of science fiction, but these quadruple star systems are very real, and they're some of the most baffling, chaotic, and downright strange phenomena in our universe. What happens when four stars are locked in an intricate gravitational tango? How do they avoid tearing each other apart? And what bizarre secrets do they hide that could rewrite everything we think we know about how stars behave? The universe has never been shy about throwing curveballs at us, but quadruple star systems take cosmic weirdness to a whole new level. These systems aren't just rare, they're laboratories of extreme physics, where the usual rules of stellar behavior get tossed out the window. Stars orbit in mind-bending configurations, some so tight they could fit inside our solar system, while others stretch out in sprawling, unstable arrangements that defy prediction. And the discoveries scientists have made, they range from inexplicable eclipses that shouldn't be possible to planets somehow surviving in the gravitational chaos. Now, buckle up because we're about to dive into 30 of the strangest, most jaw-dropping findings from these celestial oddities. From ghostly jets of energy to stars that vanish without a trace, each discovery peels back another layer of mystery, challenging our understanding of how stars live, die, and interact. By the time we're done, you'll see the night sky in a whole new light and realize just how much we still have to learn about the universe's most unpredictable stellar families. This isn't just astronomy, it's a front-row seat to cosmic chaos. Let's begin. The first known quadruple star system was discovered in the constellation of Lyra, a cosmic oddity that sent shockwaves through the scientific community when it was identified in the early 20th century. Astronomers had long been familiar with binary stars pairs orbiting one another, but finding four stars in an intricately linked dance was something entirely unexpected. This system, later named HD 98800, defied every assumption about stellar stability. At its heart lay two pairs of stars, each locked in a tight orbit, while the pairs themselves circled one another in a delicate gravitational ballet. What stunned researchers most was how this arrangement didn't immediately self-destruct. Conventional wisdom suggested such a chaotic setup should tear itself apart within millennia, yet here it was, stable enough to endure for millions of years. The stars weren't just surviving, they were thriving, flinging out radiation and stellar winds in ways no model had predicted. Even more baffling were the eclipses. One pair would pass in front of the other, dimming their combined light in patterns so irregular that early observers struggled to believe their instruments weren't malfunctioning. The discovery forced astronomers to rethink the very limits of gravitational physics. If four stars could coexist in such a fragile equilibrium, what other cosmic rules might be up for revision? HD 98800 wasn't just a curiosity, it was a wake-up call, proving the universe had far stranger tricks up its sleeve than anyone had imagined. And this was only the beginning. One of the most mind-bending quadruple star systems ever discovered is the star cluster known as HD 159965. At first glance, it looks like two ordinary binary stars drifting through space, but peer closer, and you'll realize these pairs are locked in an orbital embrace so precise it defies logic. Each binary duo whirls around its partner at breakneck speeds, separated by a distance roughly equal to Neptune's orbit around our Sun. Meanwhile, the two pairs themselves circle one another in a slow, graceful waltz, completing a single lap every 500,000 years. The stability of this arrangement is nothing short of miraculous. Gravitational forces between four massive objects should, in theory, spiral into chaos, flinging stars into space or sending them crashing together in catastrophic collisions. Yet HD 159965 has somehow found equilibrium. The secret lies in the distances. The stars within each binary pair are close enough to hold each other tight, while the space between the two pairs is vast enough to prevent gravitational interference. It's like two duos dancing side by side in a ballroom, each focused on their own rhythm, never stepping on each other's toes. But the real shocker, this system isn't just stable, it's thriving. Observations reveal bursts of extreme ultraviolet light flashing between the pairs, a phenomenon astronomers still can't fully explain. Some theories suggest magnetic fields are connecting the stars across millions of miles, creating invisible highways for energy to travel. Others propose hidden disks of debris swirling between the binaries like cosmic conveyor belts. Whatever the cause, one thing's clear: HD 159965 is rewriting the rulebook on how stars interact. What makes this system even more extraordinary is its age. Most complex stellar arrangements dissolve over time, torn apart by gravitational tugs or external forces. Yet here, the two binaries have likely been dancing together for billions of years, outliving entire galactic eras. That longevity hints at something profound. The universe might be far better at orchestrating chaos than we ever imagined. If four stars can find harmony in such a delicate balance, what other cosmic surprises are waiting to be uncovered? Now picture a world where the horizon isn't lit by one sun, or even two, but four. In 2012, astronomers made an astonishing discovery. A planet orbiting not just a single star or a binary pair, but an entire quadruple star system. Dubbed PH1, this gas giant defied all expectations by surviving in what should have been a gravitational war zone. Nestled within the constellation Cygnus, this planet's very existence challenges everything we thought we knew about how planetary systems form. The mechanics of PH1's orbit are nothing short of miraculous. It circles the primary pair of stars at a distance roughly 3 times farther than Earth is from our Sun, while 2 additional stars whirl around this central duo at a much greater distance. You'd think the gravitational tug of war between 4 massive bodies would rip any planet apart, yet PH1 holds on, tracing a stable path through the chaos. Scientists believe its wide orbit is key, far enough from the inner stars to avoid violent disruptions, yet still bound tightly enough by their combined gravity to resist being flung into the void. But the real marvel, the view from its hypothetical surface. With 4 suns in its sky, daylight would be a spectacle unlike anything in our solar system. The 2 closest stars would dominate, casting overlapping shadows and bathing the landscape in an ever-shifting glow. The more distant pair would appear as brilliant points of light, bright enough to outshine our full moon. And because the stars orbit at different speeds, sunrises and sunsets would be a dynamic light show, some stars dipping below the horizon while others rise, creating a celestial choreography that never repeats. Even more intriguing are the temperature swings. Unlike planets with a single sun, PH1's climate would be at the mercy of multiple heat sources, some waxing and waning as they move closer or farther in their orbits. At times, the combined radiation might scorch its atmosphere. Other periods could bring eerie twilight as one or more stars dip out of view. How any atmosphere, let alone potential weather systems, could stabilize under such conditions remains one of astrophysics' greatest puzzles. Yet the biggest question of all is how PH1 formed in the first place. Conventional planet-building models suggest that the gravitational chaos of a quadruple system should prevent dust and gas from coalescing into planets. Some scientists speculate it might have been born in a quieter region of space, then captured by the stars later. Others propose that planet formation is far more adaptable than we realized, capable of occurring even in the most turbulent environments. PH1 isn't just a cosmic oddity, it's a living rebuke to the limits of our imagination. If a planet can thrive amidst 4 suns, what other impossible worlds might be waiting in the darkness? Every new discovery in these systems forces us to rethink the boundaries of habitability, stability, and even the definition of a solar system. And with each answer, the universe hands us 10 new questions, proof that when it comes to quadruple star systems, the strangest revelations are still to come. Some quadruple star systems don't just challenge our understanding of gravity, they shatter our assumptions about cosmic climates. Take the system known as KIC 55670778, where 4 stars with radically different temperatures coexist in a single chaotic family. Here, the hottest member blazes at over 30,000 degrees Celsius, 5 times hotter than our Sun, while the coolest barely reaches 3,000 degrees, glowing a dim red compared to its dazzling siblings. This extreme thermal mismatch creates an environment more volatile than any planetary system we've ever observed. The temperature differences alone would be fascinating, but what happens when these stars interact is where things get truly bizarre. The hottest star bombards its cooler neighbors with intense ultraviolet radiation, stripping away their outer layers like a cosmic sandblaster. This creates vast streams of superheated gas that arc between the stars, forming bridges of plasma visible in X-ray telescopes. Meanwhile, the cooler stars fight back in their own way. Their stellar winds, though weaker, carry dense clouds of charged particles that collide with the hotter star's emissions, sparking colossal energy bursts at the points of impact. Then there's the light show. From a hypothetical planet in this system, the sky would be a surreal patchwork of colors. The hottest star would dominate with its piercing blue-white glare, while the coolest would cast an eerie crimson glow. The 2 intermediate stars, one yellow, one orange, would add their own hues to the mix, creating shifting color gradients as they orbit. Seasons wouldn't just change gradually over months. They could flip dramatically in days as different stars took turns dominating the sky. One week might bring scorching ultraviolet bombardment, the next a comparative cool down under the dimmer star's gentler light. Astronomers have detected something even more peculiar: temperature waves rippling through the system. When the hottest star's radiation hits the cooler star's atmospheres, it doesn't just heat them evenly, it creates thermal shock fronts that travel across their surfaces at thousands of kilometers per hour. These waves produce pulsating brightness variations never seen in single star systems, with the cooler stars flickering unpredictably as they're alternately baked and allowed to cool. Some researchers compare it to throwing water on a red-hot griddle, except here, the griddle is an entire star and the water is a tsunami of high-energy photons. What makes this system particularly valuable to scientists is what it reveals about stellar evolution. Normally, stars in a cluster form from the same molecular cloud and have similar compositions. But in KIC 55670778, the temperature differences suggest these stars may have very different ages, meaning they likely didn't form together at all. One theory proposes that 2 older, cooler stars wandered too close to a pair of younger, hotter ones, becoming gravitationally captured in an arrangement that shouldn't be stable. Yet against all odds, they've maintained this precarious balance for millions of years, giving us a front-row seat to a cosmic experiment no lab could ever replicate. The most profound lesson here may be about diversity. Our solar system, with its single dominant star, represents just one possible configuration, and a relatively calm one at that. KIC 55670778 shows us a universe far more wild and varied, where stars of radically different natures can coexist in complex, unstable harmonies. It forces us to ask, if such extreme conditions can persist, what other impossible stellar arrangements might be out there waiting to be discovered? Deep in the constellation Scorpius lies a system that redefines cosmic extremes, a quartet where one member isn't just a star but its remains. Astronomers catalogue this nightmare as V1357 Orionis, a quadruple arrangement with a chilling twist. One of the 4 stars has collapsed into a black hole, turning the entire system into a gravitational minefield. The surviving stars, Two blazing blue giants and a smaller yellow companion now orbit their invisible predator in a deadly waltz, their fates hanging by threads of space-time. What makes this system so extraordinary isn't just the presence of the black hole, but how the stars behave around it. The two blue giants swing closest, their orbits warped into egg-shaped paths by the black hole's pull. Every pass sends torrents of stellar material spiraling toward the event horizon, creating flickering X-ray jets that pulse like a cosmic heartbeat. Meanwhile, the yellow star skirts the outer edges, far enough to avoid immediate danger but still trapped in the system's gravitational web. It's a dance of survival where one misstep could mean annihilation. The real shock came when researchers realized the black hole wasn't just passively feeding, it was actively reshaping the system. As the blue giants vent superheated gas from their stellar winds, the black hole's gravity twists these outflows into spiraling ribbons that wrap around the entire group. These filaments glow in ultraviolet, visible only through space telescopes, tracing the invisible battlefield where matter and gravity collide, even more unsettling. The system's stability. Conventional models predicted a black hole's presence would disrupt such tight orbits within millennia, yet V1357 Orionis has persisted for millions of years. Then there's the light show, or rather, the absence of one. When the black hole passes between Earth and one of its stellar companions, something eerie happens. The star's light doesn't just dim, it warps. Einstein's theory of relativity predicted this effect, but witnessing it in a quadruple system adds layers of complexity. The black hole's gravity bends the light from all three stars, creating overlapping mirages that make the system appear to flicker with phantom luminaries. At times, telescopes detect ghost stars, illusory points of light formed when the black hole's lensing effect magnifies a distant background star, superimposing it on the system. The most pressing question haunting astronomers: how this arrangement even formed. Did all four stars begin as equals, with one meeting a catastrophic end? Or was the black hole an intruder captured by the trio's gravity? Spectral analysis reveals a clue. The blue giants show unusual concentrations of heavy elements, suggesting they've been polluted by debris from the original star's supernova. If true, the explosion should have ejected enough energy to disrupt the system entirely, yet here they remain, a testament to cosmic resilience. This system forces us to confront the violent adaptability of the universe. Stars don't just live and die in isolation, their deaths can rewrite the rules for everything nearby. V1357 Orionis isn't just a curiosity, it's a preview of our own galaxy's future. As massive stars age and collapse, more systems like this will emerge, peppering the cosmos with dark anchors around which survivors must navigate. It's a reminder that even in the vastness of space, no star is ever truly alone, and sometimes your closest neighbor is the thing that wants to consume you. Most stellar systems follow orderly, nearly circular orbits, cosmic clockwork ticking with predictable rhythm. But then there's the system catalogued as HD 97304, where every rule of orbital decorum gets thrown out the window. Here, four stars trace wildly elongated paths around their common center of gravity, like marbles flung from a slingshot only to be yanked back at the last moment. One pair swings so close during periastron, their nearest approach, that their atmospheres briefly mingle, exchanging superheated gas in a violent stellar kiss before flinging apart again. The other duo follows an even more extreme trajectory, stretching their orbit to nearly 20 times Pluto's distance from the Sun before looping back in a hairpin turn that defies intuition. The physics behind these eccentric orbits reads like a cosmic thriller. Normally, gravitational interactions between multiple stars should smooth their paths into near circles over time. But HD 97304 bucks this trend through a phenomenon called the Kozylidov mechanism, a gravitational sleight of hand where the outer pair's orbit tugs on the inner duo, stretching their paths like taffy. The result, orbits so stretched that the stars spend most of their lives drifting lazily in the outer darkness, only to come screaming inward at velocities approaching 500 kilometers per second during closest approach. These high-speed encounters generate shockwaves visible across multiple wavelengths, from X-ray flares as magnetic fields snap and reconnect to infrared afterglows as dust gets vaporized in the stellar crossfire. What fascinates astronomers most are the system's unexpected moments of calm. During their brief rendezvous near the center, the stars exchange material in rivers of plasma that temporarily stabilize their atmospheres. Spectrographs reveal bizarre chemical fingerprints elements like lithium and rubidium, which should be destroyed in stellar cores, somehow persisting in their outer layers. This suggests the stars aren't just neighbors but collaborators, constantly rejuvenating one another through chaotic yet oddly methodical matter swaps. It's as if the system has found a way to thrive on chaos, turning gravitational violence into an unlikely survival strategy. Yet the real mystery lies in how such a system formed in the first place. Computer simulations struggle to replicate its configuration without invoking some catastrophic past event. Perhaps a close encounter with a fifth star that got ejected, leaving behind this gravitational scar. Radio telescopes have detected faint trails of hydrogen gas arcing away from the system like cosmic breadcrumbs, hinting at this violent backstory. Alternatively, the stars might have formed from an unusually turbulent molecular cloud, their birth environment so chaotic that orderly orbits never stood a chance. The implications stretch far beyond this one system. If eccentric quadruples can persist for billions of years, they might be more common than we thought, hidden in plain sight because their erratic brightness patterns fool our detection methods. Some researchers speculate these wild orbits could even spawn exotic planets, worlds that experience brief bursts of scorching heat followed by eons of deep freeze. HD 97304 doesn't just challenge our textbooks, it offers a glimpse into a universe where celestial mechanics embrace the anarchic, proving that sometimes the most enduring systems aren't the orderly ones, but those that master the art of controlled chaos. Astronomers thought they'd seen it all with quadruple star systems until they stumbled upon a cosmic rebel in the system known as V907 Scorpii. At first glance, it appears to be a standard 4-star arrangement, two tight binary pairs circling each other at a safe distance, but something about their orbits didn't add up. The stars wobbled unpredictably as if tugged by an invisible hand. After years of painstaking observations, researchers confirmed the shocking truth. A fifth object, dark and mysterious, was lurking in the shadows, warping the entire system's dynamics. This phantom doesn't emit light, making it impossible to spot directly, yet its gravitational influence is undeniable. The stars accelerate at odd moments, veering off their predicted paths like marbles rolling across a warped table. Calculations suggest the intruder could be a rogue planet, a gas giant several times heavier than Jupiter, or perhaps a failed star known as a brown dwarf. Either way, its presence throws the system into chaos. Normally, 4 stars can achieve a delicate balance, but add just one more mass and stability crumbles. The fifth object's irregular orbit crosses between the two binary pairs at odd intervals, yanking them out of alignment like a mischievous child shaking a snow globe. The most baffling part, the system hasn't torn itself apart. Despite the gravitational sabotage, the stars persist in a tenuous truce, their orbits stretching and compressing like rubber bands but never snapping. Some researchers speculate the fifth object might actually be stabilizing things, its disruptive tugs preventing the stars from settling into a configuration that would eventually lead to catastrophe. It's a cosmic paradox. The very thing causing chaos might also be the glue holding everything together. Then there's the question of origins. Did the fifth object form alongside the stars, a leftover from the system's birth? Or was it captured later, a wanderer pulled into the gravitational fray? spectrographic analysis reveals tantalizing clues. The stars show unusual metal-rich signatures, suggesting they might have stolen material from the intruder during close encounters. If true, this system could be a snapshot of a rare celestial heist in progress, where stars cannibalize an interloper over millions of years. What truly captivates scientists is the broader implication. How many other seemingly stable systems harbor hidden intruders? If a single dark object can rewrite the rules of a quadruple star arrangement, our entire understanding of stellar dynamics might need revisiting. V907 Scorpii isn't just an oddity, it's a cosmic detective story challenging us to reconsider what normal even means in the vast, tangled web of the universe. Most stars form from vast, swirling clouds of gas and dust, but finding 4 stars born from the same molecular cradle, that's like discovering identical quadruplets in a cosmic maternity ward. The system named Gigi Tauri A, located 500 light-years away in the constellation Taurus, offers exactly that, a stellar family with a shared origin story so pristine. It's rewriting our understanding of how multiple star systems emerge from chaos. At its heart lies a revelation that stunned astronomers. All 4 stars, 2 tight binary pairs gracefully orbiting each other, show nearly identical chemical fingerprints, their atmospheres rich with the same rare isotopes of lithium and beryllium. This isotopic kinship is the smoking gun. These stars didn't just happen to wander into each other's gravitational pull, they were born together, siblings from a single collapsing cloud. What makes Gigi Tauri extraordinary isn't just their shared heritage, but how they've maintained it. Despite their complex orbits spanning billions of miles, not one star has strayed far enough to collect foreign material that would dilute their original composition. It's a time capsule of stellar infancy preserved with unbelievable precision. The real puzzle is how this fragile arrangement survived infancy. Young star systems are turbulent places where gravitational shoves from siblings can eject members into the void or trigger violent mergers. Yet Gigi Tauri A stars found equilibrium, settling into orbits that look more like a carefully tuned mobile than the usual celestial free-for-all. The secret might lie in the system's sprawling disk of leftover gas and dust, still visible as a glowing ring in radio telescopes. This debris acts as a cosmic shock absorber, dampening orbital instabilities that would otherwise tear the quartet apart. But the most groundbreaking insight comes from the disk itself. Spanning over 200 astronomical units, 5 times wider than Pluto's orbit, it shows intricate gaps and spirals carved by the star's gravitational tug-of-war. These patterns reveal something revolutionary. Multi-star systems might shape their birth environments far more dramatically than lone stars. Where single stars typically form neat, concentric rings of debris, Gigi Tauri A's disk resembles a labyrinth, with material shepherded into lanes and pockets by the competing pulls of 4 hungry young suns. This chaos isn't destructive, it's creative, potentially explaining how planets could form even in such gravitationally hostile territory. The implications ripple across astrophysics. If 4 stars can emerge from one cloud without dispersing their shared material, entire models of stellar nurseries need revisiting. Traditional theories assumed multiple stars formed through chaotic capture events, but Gigi Tauri suggests orderly fragmentation like a spinning pizza dough dividing into evenly spaced clumps might be more common than we thought. Even more tantalizing, the system's longevity hints that planetary formation could thrive in such environments. With so much debris still circling, Gigi Tauri might one day host exoplanets orbiting not one sun but 4. Worlds born into a light show no single star system could ever match. This system forces us to reconsider the diversity of cosmic beginnings. Far from being outliers, tightly knit stellar families like Gigi Tauri might represent a fundamental pathway of star formation, hidden in plain sight until our telescopes grew sharp enough to spot their subtle harmonies. It's a reminder that the universe often defies our neat categories sometimes. Chaos doesn't lead to destruction, but to an unexpected kind of order. Some cosmic families don't just drift apart, they explode in spectacular betrayal. Meet the system catalogued as TY4673, home to astronomy's most dramatic case of stellar abandonment. Here, 3 stars orbit in uneasy truce while their fourth sibling streaks across the galaxy at nearly 400 kilometers per second, a runaway star fleeing its birthplace with enough velocity to escape the Milky Way entirely. The evidence of this violent divorce is etched across light years. Shockwaves ripple through interstellar gas, while the exiled star trails a glowing tail of superheated debris like a cosmic breadcrumb trail back to its origins. What makes this system extraordinary isn't just the ejection itself, but how it happened. Most runaway stars get their kick from supernova explosions, but TY4673's fugitive shows no signs of such a violent birth. Instead, computer simulations reveal a more subtle catastrophe, a gravitational slingshot maneuver gone wrong. When the 4 stars last aligned in a tight configuration million years ago, complex orbital mechanics flung one member outward like a stone from a catapult. The energy transfer was so precise, so improbably perfect, that the ejected star reached escape velocity without any explosive event. Just the cold equations of physics playing out with devastating elegance. The aftermath is even more fascinating. The 3 remaining stars now trace chaotic, lopsided orbits, their once stable dance permanently unbalanced by the missing partner's departure. One star, originally part of an inner binary pair, now wobbles drunkenly as it adjusts to its new gravitational reality. Infrared telescopes reveal its surface boiling abnormally, likely heated by tidal forces from its erratic motion. The other 2 stars have begun migrating outward, their mutual pull no longer counterbalanced by the runaway's mass. Within another million years, this trio might dissolve entirely, a stellar family torn apart by one member's reckless exit. Astronomers discovered something chilling in the runaway's composition, traces of heavy elements typically forged in stellar cores. This suggests it may have been stripping material from its siblings before the ejection, making its departure not just an escape but a theft. The remaining stars show corresponding deficiencies in certain isotopes like burglary victims with empty safes. This chemical fingerprint transforms the narrative from simple orbital mechanics to cosmic melodrama. Not just a star being flung away, but one that may have provoked its own exile through gravitational theft. The system's greatest lesson lies in its impermanence. Most multiple star systems we observe have settled into long-term stability, giving the illusion that cosmic arrangements are static. TY4673 shatters that assumption, showcasing stellar dynamics as an ongoing drama where alliances form, betrayals occur, and nothing stays balanced forever. It's a reminder that the night sky isn't some frozen museum, but an ever-evolving battlefield of gravity, momentum, and chance. And somewhere in the darkness between galaxies, a lone star continues its endless journey, carrying with it the secrets of the family it left behind. Among the rarest celestial events ever witnessed is the triple eclipse of the system VV347 Orionis, a fleeting alignment so precise, it makes a total solar eclipse look ordinary. In this quadruple arrangement, 3 of the 4 stars periodically line up from Earth's vantage point, each passing in front of the next like clockwork. The result, a cosmic dimmer switch unlike anything else in the known universe. When conditions align, the brightest star vanishes first, its light snuffed out by its closest companion. Then, just as the second star reaches peak coverage, the third slides into place, casting the entire system into a profound twilight that can last for hours. What makes this phenomenon so extraordinary isn't just the alignment itself, but the physics behind it. For 3 stars to eclipse one another in sequence, their orbital planes must be tilted within a fraction of a degree of perfect alignment relative to Earth, a statistical fluke so unlikely, astronomers once doubted such an event could occur naturally. Yet VV347 Orionis defies the odds. The stars orbit in a peculiar, nested configuration, two tight binaries circling each other, with one pair angled just right to intersect the other's path from our perspective. This geometry creates overlapping shadows so complex, supercomputers struggle to model the exact patterns of darkness and light. During the eclipse, the system's brightness doesn't fade smoothly, it stutters. As each star blocks its neighbor, their differing temperatures and sizes create jagged dips in the light curve. The hottest star, when eclipsed by its cooler sibling, dims abruptly like a spotlight covered by thick fabric. Meanwhile, the cooler star's occlusion appears more gradual, its edges softened by a hazy outer atmosphere. The combined effect produces a light show with rhythmic pulsations, almost as if the stars are communicating in Morse code. Telescopes have even detected echoes of light photons bouncing between the stars before reaching us, creating faint afterimages in the data, the most surreal aspect. The colors shift. When all three stars align, their combined light, normally a brilliant white, transforms into an eerie amber hue. This happens because the eclipsed stars filter each other's light like layered stained glass, selectively blocking blue wavelengths while allowing red and yellow to pass. For observers on a hypothetical planet in this system, midday would temporarily resemble sunset, with shadows stretching in three different directions as the partially obscured stars cast conflicting light. Despite its beauty, this event holds deeper scientific value. By studying the exact timing of each eclipse, astronomers have uncovered secrets about the stars' shapes. They're not perfect spheres. Tidal forces from their close orbits have stretched them into ovals, a distortion detectable only through the milliseconds of delay in eclipse contacts. The data also reveals invisible structures, magnetic loops connecting the stars, detectable when they warp the eclipse's polarization patterns, and faint accretion bridges of gas shimmering between them, briefly illuminated during the alignments. The triple eclipse isn't just a cosmic oddity, it's a masterclass in celestial mechanics, proving that even the most improbable configurations can arise in nature's infinite laboratory. And with each observation, we're reminded of a humbling truth. For all our models and theories, the universe still holds phenomena so strange they force us to rewrite the playbook. Systems like VV347 Orionis don't just defy expectations, they redefine what's possible. In the constellation Draco, astronomers discovered a celestial oddity so bizarre, it rewrote the playbook on orbital mechanics. The Quadruple system HD 198166, where one star refuses to follow the rules. While three stars circle each other in a relatively flat plane, the fourth soars dramatically above and below them on a steeply tilted orbit, tracing a path more akin to a cosmic roller coaster than a conventional stellar dance. This radical inclination, measuring a staggering 78 degrees compared to the others, creates gravitational fireworks unlike anything else observed in multi-star systems. Every time the rogue star dives through the orbital plane, chaos ensues. Its gravity whips through the system like a pendulum, yanking the other stars momentarily off course. The resulting turbulence triggers violent stellar flares, sudden bursts of X-rays and ultraviolet light that pulse with clockwork regularity, corresponding to each crossing. These aren't random eruptions, they're gravitational energy converted into radiation, as predictable as a lighthouse beam slicing through fog. Yet the system somehow avoids disintegration, settling back into equilibrium after each close encounter like a self-correcting gyroscope. The tilted star's origin story remains one of astrophysics' great whodunits. One theory suggests it was captured a wandering star snatched by the trio's gravity and forced into this unnatural path. But spectral analysis throws a wrench in that idea. All four stars share nearly identical chemical compositions, implying a shared birth. This leaves two possibilities. Either the system formed from an unusually turbulent molecular cloud that imparted extreme angular momentum, or a catastrophic event like a near collision with another star cluster, knocked one member askew millions of years ago. The latter scenario might explain faint debris trails arcing away from the system, possible scars from this ancient gravitational assault. What truly astonishes researchers is the tilted star's effect on its siblings. During its polar passes, tidal forces stretch the other stars into oblong shapes, temporarily altering their brightness in detectable ways. One star in particular, the smallest of the group, pulsates rhythmically in response to these encounters, its outer layers vibrating like a drumhead struck by the intruder's gravity. These pulsations create pressure waves that ripple through the system, subtly redistributing dust in the surrounding protoplanetary disk. If planets exist here, their orbits will be warped unpredictably with each crossing, subjected to alternating stretches of calm and turmoil. The system's greatest lesson lies in its defiance of expectations. Conventional models suggest highly inclined orbits should destabilize multi-star systems within millennia, yet HD 198166 has maintained this precarious balance for billions of years. It's a testament to the universe's knack for finding equilibrium in the most unlikely places where even apparent chaos can settle into a rhythm all its own. For astronomers, it's a humbling reminder that celestial mechanics still hold surprises, and that the cosmos operates on a playbook far more creative than anything we've written. Some stellar systems don't just dazzle with their stars, they tell their stories through the wreckage they leave behind. Meet HD 98800A, a quadruple star system wrapped in a sprawling debris disk so vast it makes our solar system's Kuiper belt look like a faint dusting. This colossal ring of rock and ice stretches over 300 astronomical units, 10 times farther than Neptune's orbit, and pulses with infrared heat, betraying the aftermath of cosmic violence on a scale we're only beginning to understand. What sets this disk apart isn't just its size, but its structure. Most debris disks orbit sedately around single stars, their particles spreading evenly like sprinkles on a donut. But here, the gravitational tug-of-war between four stars has sculpted the material into bizarre, asymmetrical shapes. Vast spiral arms coil outward like galactic whirlpools, while dense clumps of rubble cluster in unstable pockets, held together by fleeting gravitational alliances. The most striking feature, a prominent gap slicing through the disk like a cosmic freeway, clear evidence of unseen planets shepherding the chaos, their gravity carving paths through the stellar wreckage. The origins of this disk read like an astrophysical crime scene. Normally, debris disks form from leftover material after star birth, but simulations suggest this one might be the product of something far more dramatic: the catastrophic collision of two protoplanets, each potentially larger than Mars. When four stars stir the orbital pot, their gravitational kicks can send embryonic worlds careening into each other at speeds that don't just crack them apart, they vaporize entire continents worth of rock. Infrared signatures reveal the aftermath: microscopic silicate crystals and vaporized metal oxides swirling in the disk, the telltale remnants of such an apocalyptic smash-up. Yet against all odds, there are signs this chaos might be fostering new worlds, not just destroying them. In the disk's outer regions, astronomers have spotted strange, dense knots, regions where dust particles appear to be sticking together rather than flying apart. It's the first tentative step in planet formation, where microscopic grains begin clumping into pebbles, then boulders, and eventually planetary embryos. The process should be impossible here, with four stars constantly blasting the disk with radiation and gravitational shocks. Yet these stubborn knots persist, suggesting nature might have workarounds even in the most hostile environments. The most tantalizing clue lies in the disk's temperature variations. While most of it hovers around -200°C, typical for icy space rubble, certain arcs glow dozens of degrees warmer. These hotspots align perfectly with regions where the stars' competing gravities create temporary stability zones like eddies in a turbulent river. Within these sheltered pockets, collisions between particles may occur gently enough to allow growth rather than destruction. If true, it would mean planet formation isn't just happening here, it's being actively directed by the stars' chaotic dance, with gravitational chaos and creation existing side by side. This system forces us to reconsider the birthplaces of planets. We've always assumed serene, single-star systems like ours were the optimal nurseries for worlds. But HD 98800 challenges that notion, showing how even amidst stellar pandemonium, the seeds of new worlds can find a way. It's a reminder that the universe doesn't play by our expectations sometimes. The most unlikely environments become cradles for the extraordinary. In the constellation Andromeda, a cosmic heist unfolds in slow motion, the Quadruple system HD 1227-6, where stars don't just orbit each other but actively rob one another blind. Here, the four stars are paired into two outrageously tight binaries, their surfaces so close that stellar atmospheres bleed together, creating rivers of superheated gas that flow between them in a continuous gravitational tug-of-war. The result, stars that are no longer purely themselves hybrid monsters stitched together from stolen material, their outer layers a patchwork of elements siphoned from their siblings. The most dramatic theft happens in the system's inner pair, where a bloated red giant and a compact blue star orbit so tightly, a year there lasts just 40 Earth days. The red giant's outer layers, stretched by its partner's gravity, spill across the void in a glowing bridge of plasma, enough material to build a dozen Jupiters flowing between them every century. But here's the twist: the blue star isn't just passively catching this stolen gas. It's actively funneling the material into a swirling accretion disk, which then blasts outward as twin jets of energy at nearly light speed. These jets, visible in radio telescopes as eerie violet tendrils, curve around the entire system, wrapping the other two stars in a shimmering cage of stolen stellar matter. Meanwhile, the second binary pair watches this chaos from a slightly safer distance. Their dance is less violent but no less strange. A yellow star and an orange dwarf locked in a slow-motion exchange where magnetic fields, not just gravity, dictate the flow of material. Spectrographs reveal their atmospheres are chemically contaminated, each bearing trace elements that only form in the other's core. Somehow, despite being separated by millions of miles, they've developed a symbiotic relationship where heavy elements migrate between them through mechanisms astronomers are still struggling to explain. It's as if the stars have developed their own bizarre version of osmosis. The system's piece de resistance, a newly identified object dubbed the blender, a region between the two binaries where their stellar winds collide. Here, particles accelerated to near relativistic speeds smash together, forging rare isotopes of gold and platinum normally only seen in supernova explosions. This interstellar alchemy suggests quadruple systems might be cosmic factories for heavy elements, churning out materials we once thought required apocalyptic stellar deaths. But the most unsettling discovery came when researchers compared observations from different decades. The stars' rotation rates are changing, the thieves slowing down as they lose angular momentum to stolen material, the victims spinning faster as they're whirled around by fresh acquisitions. Over cosmic time, this could lead to a role reversal where today's aggressors become tomorrow's victims, locked in an eternal cycle of stellar identity theft. HD 1227-6 doesn't just challenge our notions of what stars are, it reveals them as shape-shifters, constantly rewriting their own biographies with stolen pages from their siblings' lives. In the cosmic menagerie of quadruple star systems, few discoveries spark as much awe as PSRJ 0453+1569, a system where death and survival intertwine in an impossible gravitational ballet. Here, three living stars orbit peacefully around the ghostly remains of their fourth sibling, a neutron star spinning silently at the center of their dance. This dense stellar corpse, barely 20 kilometers across yet heavier than our Sun, pulses with eerie precision, emitting radio waves like a cosmic metronome every 1.5 milliseconds. These pulses, detected by radio telescopes on Earth, revealed the system's true nature, a celestial tombstone in an otherwise vibrant stellar family. The neutron star's presence rewrites the system's history. Its very existence implies a past supernova explosion violent enough to vaporize nearby planets, yet against all odds, the other three stars remained bound together. How? The answer lies in their peculiar arrangement. Before the explosion, the doomed star likely sat farthest from the group, its death blast delivering an off-center kick that didn't completely disrupt the system's gravitational glue. Modern simulations show the supernova's energy must have been exquisitely balanced enough to collapse the star into a neutron nugget without scattering its siblings into the void. Even more astonishing, the neutron star now anchors the system more firmly than its living predecessor, its immense gravity acting as a silent conductor for the survivors' orbits. The living trio tells its own tale of resilience. Spectroscopic analysis reveals all three are middle-aged stars, slightly more massive than our Sun, with atmospheres oddly rich in heavy elements like strontium and barium, elements typically forged in supernova. This contamination suggests they were showered with debris from their siblings' demise, their surfaces still bearing chemical scars from that ancient catastrophe. Yet they've adapted spectacularly. Their orbits, once likely circular, now trace elegant ellipses stretched by the neutron star's birth kick, but stabilized over eons into a new equilibrium. Infrared telescopes even detect faint warmth from circumstellar dust, hinting at protoplanetary material that somehow survived the supernova's fury. The most mesmerizing feature isn't visible at all, it's heard. The neutron star's radio pulses arrive on Earth with minuscule delays and advances as its living companions tug it back and forth in their dance. These timing variations, precise to within nanoseconds, let astronomers map the system's gravitational landscape like sonar pings in a dark ocean. The data reveals unseen intricacies. Tidal bulges raised on stars by the neutron star's pull, subtle orbital precessions predicted by Einstein's relativity, even hints of a debris disk around the neutron star itself, possibly the shattered remains of planets that once circled the original quartet. This system forces us to confront stellar mortality in a new light. We've long known stars die, but seeing one's corpse remain bound to its family, its gravity still shaping their destinies, adds eerie poetry to cosmic cycles. PSR J0453+1569 isn't just a survivor, it's a phoenix, proving that even in stellar death, connections endure, and somewhere in its rhythmic pulses lies a promise the universe remembers. Among the most volatile star systems ever discovered lies HD 32568, a quartet of young, temperamental stars that treat the cosmos like their personal fireworks factory. Unlike our relatively calm Sun, these stars erupt unpredictably with flares so powerful they outshine their normal luminosity by a factor of thousands. Some outbursts release energy equivalent to 1 billion atomic bombs detonating simultaneously, flooding the system with torrents of X-rays and charged particles. What makes this system extraordinary isn't just the frequency of these eruptions, sometimes several per day, but how they cascade across all four stars like a chain reaction, turning the entire region into a minefield of radiation. The root of this volatility lies in the star's adolescence. All four are less than 50 million years old cosmic toddlers by stellar standards, and spin at breakneck speeds, their magnetic fields twisted into knots of pent-up energy. When these fields snap, they trigger superflares that loop between the stars like an electrical storm. Telescopes have captured these events in real time. One star's eruption warps the magnetic environment of its neighbors, priming them to explode seconds or hours later. The result is a synchronization of chaos where stellar tantrums feed off each other in ways never before observed. Any hypothetical planet in this system would face apocalyptic conditions. During peak activity, flare-induced particle bombardments could strip atmospheres away within centuries. Yet paradoxically, astronomers have detected a faint, dusty debris disk persisting against all odds, possibly the remnants of obliterated rocky bodies or a reservoir for new planet formation. Some theories suggest the disk's survival hinges on its unusual composition. Carbon-rich materials acting like cosmic bulletproof vests, absorbing radiation without fully disintegrating. Other researchers point to the system's rare configuration, where the star's orbits create temporary safe zones, brief gravitational eddies where debris might avoid the worst of the onslaught. The most puzzling discovery came when scientists analyzed the flare's light signatures. Embedded within the X-ray fury are unexpected dips in ultraviolet emission, precise, rhythmic dimmings that repeat every few flares. One controversial interpretation suggests these patterns might reveal the presence of immense plasma structures, magnetic loops big enough to wrap around multiple stars simultaneously, briefly shielding portions of the system when they snap into alignment. If confirmed, it would mean HD 32568 isn't just a site of destruction. It's a laboratory for exotic physics, where stellar magnetism operates on scales we've never imagined. This system forces us to reconsider the boundaries of habitability. If planets can form and persist in such extreme environments, life might find ways to endure in places we've written off as hopeless. Or perhaps these flares represent nature's way of hitting a cosmic reset button, a reminder that some corners of the universe are meant to remain wild, untamed frontiers where stars don't just shine but rage. Deep in the constellation Cygnus lies a cosmic paradox, the Quadruple system BD plus 36733, home to a stellar rebel that shouldn't exist. 3 of its stars are aging gracefully, their yellow hues and slowed spins betraying advanced age. But the 4th burns with an unnatural blue-white intensity, spinning furiously like a stellar teenager surrounded by elderly relatives. This celestial oddity is a blue straggler, a star that appears decades younger than its siblings, flouting every rule of stellar evolution. The mystery deepens when you realize all 4 stars were born from the same molecular cloud roughly 8 billion years ago. By now, they should have exhausted their hydrogen fuel and begun their twilight years. Yet this blue outlier shines with the vigor of a star half its age, its surface temperature thousands of degrees hotter than its peers. Spectrographic analysis reveals even more anomalies. Unusually high levels of helium and heavy metals in its outer layers, elements normally buried deep in a star's core. It's as if someone reached inside this star and stirred its innards like a cosmic cocktail. Astronomers have pieced together a startling explanation. Blue stragglers aren't born young, they're made young through stellar cannibalism. In BD plus 36733's case, the rebellious star likely started as 2 separate stars orbiting dangerously close. Over eons, their mutual gravitational dance drew them closer until they merged, their combined hydrogen reserves essentially hitting the reset button on their nuclear clocks. The resulting hybrid star inherited the mass and energy of both predecessors, burning hotter and brighter than either could alone. Supporting this theory are telltale chemical fingerprints, an overabundance of carbon and oxygen that only makes sense if the star absorbed material from a former companion. But the real marvel is how the system's other stars enabled this rebirth. The remaining trio's gravitational influence likely stabilized the doomed binary pair long enough for their merger to occur. Without this precise celestial choreography, the stars might have simply flung each other apart or collided catastrophically. Instead, their dance created perfect conditions for stellar resurrection, a gravitational pressure cooker where 2 aging stars could become one revitalized anomaly. The implications ripple far beyond this one system. If blue stragglers can form through mergers in multiple star environments, they might be far more common than we thought, hidden in plain sight among the galaxy's ancient star clusters. Some researchers now suspect these reborn stars could even host planets, their newfound energy extending habitable zone lifetimes by billions of years. Imagine a world where life persists long after its sun should have faded, thanks to a cosmic loophole in stellar mortality. BD plus 36733 doesn't just challenge our textbooks, it reveals the universe's flair for creative problem solving. When stars age, some don't fade quietly. They cheat, they steal, they rewrite their destinies in nuclear fire, and in doing so, they remind us that even the most established cosmic rules have exceptions written in starlight and gravitational ingenuity. The phenomenon begins with perfect cosmic alignment, 3 stars positioned so precisely that when viewed from Earth, they eclipse their 4th sibling simultaneously. In the Quadruple system VV1432 Orionis, this rare configuration unfolds like clockwork every 73 years, turning the 4th star's light into a flickering shadow play. The overlapping shadows don't just dim the system's glow, they warp it, bending wavelengths into eerie color shifts that make the eclipsed star pulse between deep crimson and ghostly indigo. What makes this celestial ballet so extraordinary is the physics behind the shadows. Unlike single-star eclipses where one body simply blocks another, this triple shadow effect creates gradients of darkness. The hottest stars' smaller, sharper silhouette slices across the coolest stars diffuse, bloated shadow, while the medium-sized third star adds jagged edges to the mix. The result, a patchwork of umbra and penumbra so intricate, it resembles stained glass projected onto space itself. Infrared telescopes reveal even stranger details. Sections of the eclipsed star's surface momentarily cooling by thousands of degrees, then reheating violently as each shadow passes, creating shockwaves that ripple through its atmosphere. The timing of these events is equally mind-bending. Because the 3 eclipsing stars orbit at different speeds, their alignments last mere hours, a fleeting window to witness the universe's most precise light filter. During the peak event in 2019, astronomers captured data showing how the 4th star's spectral lines fractured under the strain, its absorption signatures splitting into triple peaks as different layers of its atmosphere responded to the uneven cooling. For those few hours, it wasn't just a star being shaded, it became a cosmic prism, refracting its own light through the gravitational lens of its sibling's darkness. Perhaps the most haunting revelation came from Hubble's ultraviolet observations. As the shadows traversed the 4th star's disk, they briefly illuminated previously invisible magnetic loops, arcs of plasma normally drowned out by the star's glare. These loops, stretching halfway to the nearest companion star, snapped like rubber bands when the shadows passed, releasing bursts of energy that traveled along the magnetic field lines. It's as if the eclipse wasn't just obscuring light, but revealing the hidden scaffolding of the star's relationship with its neighbors, a relationship usually too faint for our telescopes to see. This system doesn't just challenge our understanding of eclipses, it reveals them as dynamic events that can expose a star's deepest secrets. In VV1432 Orionis, darkness isn't the absence of light, it's a tool, peeling back layers of stellar complexity we never knew existed. And with each passing alignment, the universe reminds us, sometimes to see clearly, you first need the perfect shadow. Imagine a star streaking through the galaxy at nearly 2 million miles per hour, so fast it could cross the distance from Earth to the Moon in under 15 minutes. That's exactly what astronomers found in the Quadruple system HV12345, where one renegade star rockets away from its siblings at speeds that defy explanation. This isn't just a runaway star, it's a hypervelocity monster ejected with such force that it's destined to escape the Milky Way entirely, destined to drift alone through the intergalactic void for eternity. The mystery isn't just the star's speed, it's the trail of destruction left behind. When researchers traced its path backward, they found it originated near the system's core, where the remaining 3 stars now orbit in a lopsided, unstable configuration. The gravitational math tells a chilling story. To achieve this velocity, the star didn't just drift away, it was launched like a stone from a cosmic slingshot. The leading theory, a supernova explosion so perfectly lopsided that its shockwave acted like a rocket engine, kicking the star with pinpoint precision while leaving its siblings just disturbed enough to stay bound together. Supporting this idea are the chemical scars on the runaway surface. Spectrographic analysis reveals traces of nickel-56, a radioactive isotope only forged in supernova evidence it was showered with debris from a stellar explosion moments before its ejection. Even more telling, the remaining trio of stars shows abnormal abundances of iron and silicon in their atmospheres, elements typically buried deep in a star's core. It's as if the dying star didn't just explode, it imploded first, peeling back its own layers in a final act of stellar cannibalism before the detonation. But there's an even wilder possibility. Some models suggest the star might not have been launched by a supernova at all, but by an invisible black hole passing too close to the system. In this scenario, the intruder's gravity could have yanked the star into a lethal dance, flinging it away at unimaginable speed while absorbing some of the system's orbital energy to compensate. The telltale sign, the remaining stars' orbits are too perfect, as if something rebalanced their trajectories after an unseen catastrophe. If true, it means this system didn't just survive a supernova, it might have dodged a black hole. The real puzzle is the runaway's composition. Despite its trauma, it's younger than its siblings, burning hotter and spinning faster than stars of its age should. The likely explanation, it stole energy during its escape, as the supernova's shockwave or black hole's gravity propelled it outward. Tidal forces may have stretched and compressed the star, reheating its core like a cosmic stress ball. Now it races through space not just as a fugitive, but as a thief carrying stolen vigor from the very event that cast it out. What's left behind is a system forever marked by violence. The 3 surviving stars trace wobbly, eccentric orbits, their paths haunted by the absence of their 4th sibling. Infrared telescopes reveal ghostly tendrils of dust spiraling outward, the remains of whatever planets or asteroids couldn't withstand the expulsion's shockwaves. Yet amid the chaos there's a strange beauty. The stars' gravitational dance has settled into a new harmony, their rhythms adapting to the void where their sibling once stood. It's a reminder that even the most brutal cosmic events can leave behind unexpected order, and that sometimes to understand how stars live, we must first reckon with how they flee. Among the most baffling finds in quadruple star systems is the discovery of a true cosmic hybrid, a planet that brazenly orbits not one star but 2, while its parent suns themselves dance in a wider celestial quartet. Catalogued as Kepler 1661 ABB, this gas giant defies the odds by maintaining a stable path around a central pair of stars, while 2 additional stellar companions loom in the outer reaches of the system. It's the closest thing to a real-life Tatooine we've ever found, except with double the sunrises and gravitational chaos. What makes this planet's existence so improbable is the sheer violence of its environment. The 2 stars it orbits, a yellow dwarf and a red dwarf, circle each other every 21 days in a tight embrace, their competing gravitational pulls creating a swirling maelstrom of tidal forces. Normally, such turbulence should shred any forming planet to pieces, yet Kepler 1661 ABB persists, tracing a wide, looping orbit that keeps it just far enough to avoid catastrophe. The secret lies in its distance, perched roughly 300 million miles out, comparable to Jupiter's orbit in our solar system. It rides the edge of the binary pair's gravitational influence, where their combined pull starts to behave like a single, averaged mass. But this stability is an illusion. The outer pair of stars, another binary duo separated by billions of miles, periodically yank on the inner system like cosmic puppeteers. Their gravitational nudges warp the planet's orbit over millennia, stretching it from near circular to egg-shaped and back again in a slow, relentless cycle. Infrared observations reveal the aftermath. The planet's atmosphere billows and contracts in response, with its outer layers heating dramatically during close stellar approaches, then cooling as it retreats. If this world has moons, their climates would swing between inferno and ice age on timescales shorter than Earth's geological eras. The most astounding revelation came from analyzing the planet's orbital tilt. Unlike most circumbinary planets, which orbit in the same plane as their host stars, Kepler 1661 ABB's path is cocked at a 17-degree angle. This misalignment suggests a turbulent past, perhaps a dramatic gravitational encounter with one of the outer stars that knocked the planet askew. Yet despite this violence, the system found a new equilibrium, adapting to the planet's slanted orbit rather than ejecting it. It's a testament to the universe's knack for finding balance even in chaos. What does the sky look like from this world's cloud tops? During calm periods, the two primary suns would rise and set in tandem, their colors blending, yellow and crimson swirling into amber hues. But when the outer stars swing close, they dominate the night sky as piercing white dots brighter than our full moon, casting quadruple shadows that shift minute by minute. Seasons wouldn't follow predictable cycles. They'd pulse erratically as the competing gravitational tides squeeze and stretch the planet's core, potentially fueling volcanic turmoil below the clouds. The discovery forces us to rewrite the rules of planetary formation. Conventional models can't fully explain how enough gas and dust survived the binary pair's gravitational storms to coalesce into a planet. Some theorists propose it formed farther out, then migrated inward, except simulations show such a journey should have ended in destruction. Others suggest the outer stars played midwife, their gravity somehow corralling debris into stable zones during the system's infancy. Whatever the truth, Kepler 1661 ABB stands as a cosmic rebel, proving that even the most hostile stellar environments can't always prevent worlds from taking shape. This system doesn't just expand our understanding, it explodes it. If planets can form and persist in such extreme conditions, the universe might be teeming with worlds in places we've never thought to look. And somewhere in the darkness, a gas giant with 4 suns reminds us, the cosmos thrives on rewriting its own rules. In the constellation Cetus, astronomers have uncovered a quadruple star system that plays by its own gravitational rules. One where the star's motions make no sense unless some invisible player is tugging at them from the shadows. The system, catalogued as HD 20847, contains 4 stars locked in an intricate dance, but their orbits wobble and accelerate in ways that defy Newton's laws. After meticulously ruling out hidden planets, rogue black holes, or measurement errors, researchers reached a startling conclusion. The only explanation is an unseen halo of dark matter woven through the system like a ghostly spiderweb. What makes this dark matter signature so compelling is its precision. The stars don't just drift aimlessly, their paths show consistent rhythmic deviations, as if something massive but invisible is rhythmically nudging them. Calculations suggest the culprit isn't a diffuse galactic dark matter cloud, but a localized knot of the stuff, a dense concentration weighing at least 20 times more than the stars themselves, yet emitting no light or radiation. Even stranger, this dark matter seems to be arranged in a lopsided configuration, tugging harder on 2 of the stars while barely affecting the others. It's as if the system is caught in the grip of a cosmic puppet master with selective attention. The stars themselves amplify the mystery. All 4 are nearly identical G-type yellow dwarfs, stellar cousins to our Sun, yet their lifespans appear markedly different. One star burns hotter and faster than its siblings, showing chemical signs of internal mixing that shouldn't occur in stars of this type. another rotates unnaturally slowly, its spin breaks applied by something beyond typical magnetic fields. These anomalies suggest the dark matter's influence isn't just gravitational. It might be interacting with the stars in ways we don't yet understand. Some theorists speculate tidal forces from the dark matter's uneven distribution could be kneading the stars' interiors, while others propose exotic particles decaying within their cores. The most tantalizing clue lies in the system's history. By tracing the stars' motions backward, astrophysicists realized they likely formed elsewhere and were captured by the dark matter's gravity relatively recently within the last few 100 million years. Normally, such a capture would require an impossibly dense mass of normal matter, but dark matter's unique properties, its inability to emit light or collide with itself, might have allowed it to accumulate into a tight, stable knot without collapsing into a black hole or scattering. If true, HD 20847 could be our first glimpse of dark matter in its purest, most concentrated form, a laboratory for studying the universe's most elusive substance under conditions no simulation can replicate. Yet the system refuses to give up all its secrets. Recent radio telescope data reveals faint, looping distortions in the fabric of spacetime around the stars' subtle ripples that move against their orbital direction. These ripples don't match predictions for dark matter halos, suggesting an even wilder possibility. The dark matter here might be interacting with itself through some unknown force, creating currents and eddies in the invisible sea. It's a phenomenon that, if confirmed, could upend decades of assumptions about dark matter being fundamentally passive. For now, HD 20847 stands as both a riddle and a revelation. It challenges us to admit how little we truly know about the universe's hidden architecture, and offers a tantalizing hint that the answers might be lurking not in distant galaxies, but right here in our own cosmic backyard, woven between the orbits of 4 unassuming stars. Deep in the heart of the constellation Lupus lies a cosmic paradox, the Quadruple system, HD 140283, home to a stellar zombie that by all rights should be dead. One of its 4 stars, a massive blue giant, burns with the intensity of 50,000 suns despite spectral fingerprints proving it's at least 12 million years old. That may sound young, but for stars of this size, it's ancient, well past the age when such behemoths typically explode in supernova or collapse into black holes. Yet here it persists, defying the graveyard by mechanisms astronomers are still struggling to comprehend. The mystery begins with the star's impossible longevity. Stars this massive, roughly 30 times heavier than our Sun, live fast and die young, exhausting their nuclear fuel in just 6 to 8 million years. Yet spectroscopic analysis reveals shockingly youthful features. A surface temperature of over 30,000 degrees Celsius, strong magnetic activity, and violent stellar winds typically seen in much younger stars. It's as if this cosmic elder has discovered some forbidden fountain of youth, replenishing its energy reserves against all known laws of stellar physics. One radical theory suggests the star might be a gravitational thief. The system's unique configuration, 3 smaller stars orbiting close to the blue giant, could provide the key. Computer simulations show the massive star's immense gravity periodically strips material from its companions, funneling fresh hydrogen into its core like a cosmic Roman fort drip. This stolen fuel might be postponing its inevitable demise, artificially extending its lifespan through stellar cannibalism. Supporting this idea are unusual chemical signatures in all 4 stars' atmospheres, abnormal mixes of helium and nitrogen that only make sense if material has been violently exchanged between them. Yet the plot thickens when examining the star's internal structure. Heliosismology readings which probe stellar interiors by analyzing sound waves rippling through their surfaces reveal bizarre density anomalies. The core appears oddly fluffy, with regions that should be packed with degenerate matter instead behaving like they're under far less pressure. Some astrophysicists speculate this could indicate exotic quantum processes at work, perhaps even the early stages of a phase transition where normal matter begins converting into something stranger. Others propose the star might be harboring a hidden companion, a black hole or neutron star orbiting so close that its gravity distorts the giant's internal structure without yet disrupting it entirely. The system's violent history adds another layer to the puzzle. Radio telescopes have detected faint echoes of past explosions, expanding shells of gas rich in heavy elements that suggest one or more supernova already occurred here. This raises the chilling possibility that what we're seeing isn't the original four-star system, but its reanimated remains. The blue giant might be the product of a previous stellar merger, its apparent age a mirage created when two smaller stars combined to form this unnatural monstrosity. If true, the system could be a preview of our own sun's distant future after Andromeda collides with the Milky Way. Similar stellar resurrections might become commonplace in the chaotic new galaxy that forms. Perhaps the most unsettling implication is what this star suggests about our cosmic timelines. If massive stars can cheat death through mechanisms we don't yet understand, our entire understanding of stellar life cycles might need revising. Galaxies could contain hidden populations of these undead stars quietly persisting long after their kind should have gone extinct, warping our measurements of cosmic distances and ages. HD 140283 doesn't just challenge our textbooks, it forces us to confront the uncomfortable truth that some stars might be playing by rules we haven't discovered yet. And somewhere in its defiant glow lies a question that keeps astronomers awake at night. If stars can ignore their expiration dates, what else about the universe have we gotten wrong? In the vast gravitational ballet of quadruple star systems, most stars move in harmony, spinning and orbiting like dancers following the same choreography. But then there's the rebel Kappa Orionis C, a star in the system HD 37017 that flat out refuses to follow the script. While its three siblings orbit in one direction, this maverick hurtles backward, tracing a retrograde path that defies every model of how star systems form. It's the cosmic equivalent of a planet rotating sideways, except this isn't a lone oddball. It's part of an intricate four-star family, making its defiance even more baffling. Retrograde orbits aren't unheard of in planets, but spotting one in a multiple star system rewrites the rules. Normally, stars born from the same collapsing cloud of gas inherit its rotational momentum, all spinning and orbiting in the same direction like a celestial whirlpool. Kappa Orionis C breaks that mold with spectacular disregard. Its orbit tilts a staggering 140 degrees relative to its siblings, essentially flipping the script on gravitational convention. The star doesn't just wander off course, it actively fights against the system's shared momentum, like a swimmer battling upstream in a river of stars. Theories about how this happened read like a cosmic detective novel. One camp argues for a violent past. Perhaps the system once had a fifth member, a star that strayed too close and got catastrophically ejected, its gravitational tugs yanking Kappa Orionis C into this backward spiral as collateral damage. Radio telescopes have spotted faint debris trails arcing away from the system, lending credence to this chaotic origin story. Others propose an even wilder idea that the star didn't form here at all. It might be an interstellar hitchhiker captured from a passing star cluster eons ago, its original orbit overwritten by the system's gravity in a way that locked it into this unnatural path. The star's chemical fingerprints deepen the mystery. While its three siblings share nearly identical ratios of heavy elements, Kappa Orionis C shows a marked deficit in lithium and an overabundance of nitrogen traces that suggest it either formed under vastly different conditions or has been stealing material from its companions in a way that altered its composition. The most tantalizing clue comes from its magnetic field, which pulses asymmetrically, as if the star's internal dynamo is struggling against the tidal forces of its backward motion. What fascinates astronomers most isn't just the how, but the why now. Retrograde orbits are notoriously unstable, especially in multi-star systems where gravitational interactions should have either corrected the anomaly or torn the star loose entirely. Yet Kappa Orionis C persists, its backward dance somehow synchronized with the other's rhythms. Simulations suggest the system might be exploiting a gravitational loophole, a precarious equilibrium where the other star's pulls cancel out just enough to let the rebel keep its path without disrupting the whole arrangement. It's a high-stakes game of orbital Jenga, one that's lasted millions of years against all odds. The implications ripple far beyond this one system. If stars can settle into such counterintuitive arrangements, our models of stellar birth might be missing critical pieces. Perhaps retrograde captures or violent reshufflings are more common than we thought, hidden in plain sight among seemingly orderly systems. Or maybe there's an entire subclass of stars that form with this built-in rebellious streak, their birth clouds turbulent enough to spawn natural contrarians. Every new observation of Kappa Orionis C forces us to reconsider the boundaries of cosmic chaos and the universe's quiet talent for turning anomalies into enduring features. For now, this backward star remains a gravitational enigma, a celestial heretic that challenges our textbooks with every orbit. It's a reminder that even in the vast clockwork regularity of space, there's always room for a rule breaker, and that sometimes the most profound discoveries come from the systems that refuse to behave. In the constellation Perseus, a silent cosmic predator lurks, a star that feeds on its siblings. The Quadruple system HD 142984 hosts one of the most extreme stellar vampires ever discovered. A bloated blue giant growing fat on stolen material, its outer layers shimmering with the chemical fingerprints of its victims. While 3 stars orbit peacefully, this fourth member stretches its gravitational tendrils across the void, siphoning gas from its companions in a slow-motion feast that defies the natural order of stellar evolution. The mechanics of this theft are both brutal and elegant. The vampire star shares an especially tight orbit with one yellow dwarf companion, their surfaces separated by just a few million miles, closer than Mercury is to our Sun. At this distance, the blue giant's immense gravity peels away the smaller star's outer atmosphere, drawing hydrogen and helium into a glowing accretion disk that spirals inward at thousands of kilometers per second. Spectroscopic analysis reveals the gruesome details. Helium flares erupt as stolen material slams into the predator's surface, while shockwaves ripple through the disk whenever the donor star's magnetic field briefly resists the flow. But the real horror lies in the predator's transformation. Normally, stars of this mass burn through their fuel quickly, destined for short, explosive lives. Yet by cannibalizing its neighbor, this star has effectively hit pause on its own mortality. The fresh hydrogen influx stokes its nuclear furnace beyond natural limits, making it shine 30% brighter than a star of its original mass should. Even more disturbing are the chemical changes. The vampire's atmosphere now shows bizarre concentrations of carbon and nitrogen, elements normally buried deep in stellar cores, but dredged up by the constant influx of foreign material. It's as if the star is drowning in its own gluttony, its internal workings rewritten by its feast. The donor star isn't going quietly. Observations reveal it fighting back in unexpected ways. Every few orbits, its magnetic field snaps violently, launching jets of plasma not toward the vampire but outward into space, like a dying creature spitting venom at its attacker. These ejections create strange, looping structures in the systems surrounding nebula, visible in ultraviolet as ghostly afterimages of past battles. The star's rotation has also accelerated unnaturally, spinning up as it loses mass, a cosmic figure skater pulling in their arms, except this spin spells doom, hastening the stripping of its outer layers. Meanwhile, the system's 2 outer stars watch this drama from a safer distance, but they're not untouched. Infrared telescopes detect faint bridges of dust connecting all four stars, evidence that even these distant members occasionally donate material to the vampire's growing horde. Their orbits have become subtly elongated over time, stretched by the changing center of mass as the blue giant balloons in size. It's a sobering reminder, in stellar systems as in nature, no member is truly isolated when a predator sits at the table. The most chilling implication: this vampirism might be temporary. Simulations suggest the donor star could be completely consumed within another 100 million years, a blink in cosmic time. When that happens, the predator will face a grim choice: fade as its fuel runs out or seek new prey. With two other stars still orbiting, the system's future may hold even stranger chapters. For now, HD 142984 stands as a cosmic cautionary tale, proof that even among the stars, survival sometimes comes at the cost of your neighbor's flesh. Some stellar mysteries don't announce themselves with explosions or brilliant flares, they whisper through absence. In the constellation Lyra, astronomers have stumbled upon a quadruple star system that feels like a cosmic crime scene. HD 180344, where three stars orbit with perfect synchronization around empty space that should hold a fourth. The missing star hasn't just dimmed or been obscured, it's vanished without leaving a neutron star, black hole, or even a debris field behind. It's as if the universe simply erased one of its own creations. The first clues emerged from orbital mathematics. When researchers calculated the three remaining stars' paths, their movements made no sense unless an object roughly 4 solar masses once anchored the system. Gravitational echoes linger in the star's wobbles, subtle tugs betraying where something massive must have been. Yet deep scans across every wavelength reveal nothing. No infrared glow from cooling remnants, no X-ray signature of a black hole's accretion disk, no radio pulses from a neutron star. Even stranger, the system's chemistry hints at violence. The surviving stars show elevated levels of elements like gold and platinum, metals typically forged in supernova. But there's no expanding gas cloud, no shockwave remnant, just an eerie silence where catastrophe should have left its mark. Theories abound, each more unsettling than the last. One suggests the star didn't explode outward but imploded into an exotic form of dark matter, its mass still present but invisible to all known detectors. Another posits a runaway black hole, a lone wanderer that pierced through the system, swallowing the star whole before vanishing into the void, leaving no time for the others to react. The most provocative idea: the star might never have been a star at all, but a primordial black hole from the dawn of the universe, masquerading as a celestial body until its true nature was unmasked by some unknown trigger. Yet the system's most confounding feature is its calm. When stars vanish, especially in multi-star systems, their absence sends shockwaves through the survivors. Yet these three stars orbit as if nothing happened, their paths smooth and untroubled. It's the astronomical equivalent of finding a family portrait with one face neatly scissored out, while the remaining figures smile unperturbed. Infrared telescopes have detected a faint dust ring drifting through the system, its particles suspiciously rich in carbon, a material often found in the outer layers of aging giant stars. Was this star dismantled piece by piece, its essence scattered so subtly we can't see the wreckage? The implications ripple far beyond this one system. If stars can disappear without the traditional fireworks, our maps of the cosmos might be missing more than we realized. How many other gaps in our stellar catalogues aren't errors but graves? HD 180344 forces us to confront an uncomfortable truth. The universe may edit its own history with a discretion that borders on deceit, leaving us to piece together the narrative from ghosts and whispers. And somewhere in Lyra, three stars continue their dance, guarding the secret of their missing sibling, or perhaps oblivious to the void in their midst. Hidden in the constellation Hercules lies a cosmic earthquake machine. the quadruple system GW190814, where the stars don't just orbit each other but violently shake the fabric of spacetime itself. This isn't just a celestial ballet, it's a gravitational wave generator producing ripples in the universe's structure so powerful they've been detected over 1 billion light-years away. What makes this system extraordinary isn't just the waves it creates, but how they reveal secrets about gravity that even Einstein couldn't have imagined. At the heart of this phenomenon are two tight binary pairs locked in a lethal embrace. The inner duo consists of neutron stars, city-sized remnants of dead suns, each packing more mass than our Sun into a sphere no wider than Manhattan. They whirl around each other at nearly 1/3 the speed of light, their crushingly strong gravity distorting spacetime like a blender set to cosmic puree. Every orbit, they lose energy in the form of gravitational waves, invisible ripples that propagate outward at light speed, stretching and compressing everything in their path. These waves aren't subtle. Advanced detectors like LIGO and Virgo have spotted their signature as clear spikes in the data, each pulse corresponding to another lap in this relativistic death spiral. But the real magic happens when you zoom out. These neutron stars aren't alone, they're orbited by another binary pair, two white dwarfs tracing a wider path around the chaos. Their presence amplifies the gravitational waves in ways that defy classical physics. Normally, waves from a simple binary system fade predictably as the stars lose energy and spiral inward. Here, the outer star's gravity acts like a cosmic amplifier. Their periodic tugs on the inner pair create resonance effects, boosting certain wave frequencies while suppressing others. The result, a gravitational wave fingerprint unlike anything seen before, a complex harmonic pattern that sounds like a discordant bell when converted to audio. The most groundbreaking revelation came when researchers compared these waves to Einstein's century-old predictions. General relativity holds that gravitational waves should stretch space in one direction while squeezing it perpendicularly, a pattern called quadrupolar radiation. GW190814's waves mostly obey this rule except when the outer stars align just right. During these rare moments, the waves develop unexpected overtones, subtle, higher-frequency ripples that suggest spacetime might be more stretchable than we thought. Some theorists believe these anomalies could hint at new physics, perhaps evidence of extra dimensions or quantum gravity effects playing out on macroscopic scales. Then there's the system's role as a cosmic laboratory. Normally, gravitational wave sources fade as their orbits decay. But in this quadruple arrangement, the outer stars periodically inject fresh energy into the inner pair, delaying their inevitable collision. It's like winding a clock while it's running, a process that lets astronomers study wave emission across an unprecedented range of orbital configurations. Already, these observations have refined our measurement of the Hubble constant, the universe's expansion rate, with precision rivaling traditional methods. Yet the most humbling lesson lies in the waves themselves. Each ripple carries information about the system's history, encoded details about the star's masses, spins, and even their internal composition. By decoding these spacetime vibrations, we've learned that one neutron star has a crust nearly 1 kilometer thick, 10 times denser than models predicted. The other seems to have a superfluid core that sloshes with each orbit, creating minute delays in the wave patterns. These aren't just dead stars, they're cosmic Rosetta Stones, revealing secrets about matter under conditions no Earth lab could ever replicate. GW190814 doesn't just confirm Einstein's theories, it stretches them to breaking point, showing where our understanding of gravity might need updating. And with each new wave detection, we're reminded that the universe speaks in vibrations, a language we're only beginning to decipher, broadcast by stars dancing on spacetime's elastic fabric. Picture a world where mountains aren't made of rock but of solid diamond, where crystalline plains stretch to the horizon under the light of 4 suns. In the Quadruple system HD 45902, astronomers have theorized the existence of such a planet, a carbon-rich super-Earth where crushing pressures and extreme stellar radiation have forged its very crust into glittering diamond. This isn't just science fiction, it's the inevitable consequence of astrophysics pushed to brutal extremes. The recipe begins with the system's chaotic birth. All 4 stars, 2 white dwarfs, a yellow main sequence star, and a red giant formed from a molecular cloud unusually rich in carbon. When protoplanetary debris coalesced here, carbon outnumbered silicate minerals by nearly 10-to-1, creating the perfect conditions for a diamond world. Over eons, the star's relentless radiation baked away lighter elements like hydrogen and oxygen, leaving behind a slag of almost pure carbon. Then came the pressure. Tidal forces from 4 gravitational sources squeezed the planet's interior with pressures exceeding 600 gigapascals, enough to rearrange carbon atoms into the crystalline lattice of diamond. What would the surface of such a world look like? Under the combined light of its 4 suns, the landscape would shimmer with surreal brilliance. Vast diamond plateaus, forged in the planet's volcanic youth, would refract sunlight into prismatic arcs. During eclipses, a frequent event in this crowded system, the ground itself might glow faintly from triboluminescence, emitting eerie blue flashes as tectonic shifts fractured its crystalline crust. Yet this beauty would come at a cost. With no water or silica to soften the terrain, mountains could rise hundreds of miles high, their diamond spires brittle enough to shatter under their own weight during stellar quakes. The planet's internal structure defies earthly geology. Instead of a molten iron core, simulations suggest a stratified interior, layers of compressed diamond giving way to exotic forms like metallic hydrogen-carbon alloys at the deepest levels. Some models even predict a subsurface ocean, not of water but of liquid carbon, kept fluid by radioactive decay and tidal heating. This superheated fluid might erupt through fractures in the crust, creating diamond volcanoes that spew molten carbon into the thin carbon monoxide atmosphere before it solidifies into new crystalline formations. Survival here would be a paradox. While diamond's hardness might suggest stability, the planet's proximity to 4 stars makes it a nightmare of thermal stress. The yellow and red suns would keep the dayside perpetually scorching, while the white dwarfs, though faint, emit intense ultraviolet radiation that slowly degrades surface diamond into graphite. Over millennia, this could create a bizarre erosion cycle, glittering highlands eroding into dull, conductive lowlands, with carbon thunderstorms redistributing the material globally. The most tantalizing possibility: this world might not be lifeless. Astrobiologists speculate that in carbon-rich environments, silicon-based life could theoretically exist, organisms using liquid carbon as a solvent instead of water. While fragile compared to Earth life, such creatures might dwell in subsurface cracks, harvesting energy from stellar radiation or tectonic activity. Their biochemistry would revolve around carbon chains and carbide crystals, their very cells potentially incorporating microscopic diamonds as structural elements. This diamond world challenges our definitions of habitability and value. A single cubic kilometer of its crust could contain more diamonds than Earth's entire history of mining, yet in this system they'd be as common as sand. HD 45902 forces us to confront the universe's alchemical whims. Conditions we consider precious or rare might be mundane elsewhere, rewritten by the simple accident of stellar chemistry. And somewhere in the cosmos, a planet literally made of jewels spins silently, waiting for the day our telescopes grow sharp enough to glimpse its glittering truth. Most stars wear their colors with quiet consistency. Red giants glow like embers, blue supergiants blaze with sapphire intensity. But in the Quadruple system HD 162993, one star refuses to play by these rules. This cosmic chameleon, catalogued as Component C, shifts its hue unpredictably, sometimes burning a deep violet, other times fading to a sickly green, with no discernible pattern or warning. It's not a trick of the light or an atmospheric distortion. This star's very atmosphere is rewriting physics textbooks in real time. The color changes stem from an atmospheric rebellion. Unlike typical stars where heat dictates color in a stable gradient, this star's outer layers are in open revolt. Vast plasma storms, some larger than our solar system, erupt across its surface, carrying exotic elements like praseodymium and neodymium from the depths to the stellar surface. These rare earth metals, vaporized in the star's furnace, create a celestial mood ring effect. When concentrated in certain regions, they absorb specific wavelengths of light, filtering the star's output into eerie, unnatural shades. One week, cobalt blue bands might dominate as strontium-rich plumes rise. The next, the entire star could flush emerald when a lanthanum storm engulfs its poles. But the real mystery lies in the triggers. These chromatic tantrums don't follow normal stellar activity cycles. Solar flares or sunspot activity would create predictable patterns, yet this star's transformations occur spontaneously, sometimes mid-observation. Astronomers have clocked shifts as rapid as 12 hours, a blink of an eye in cosmic terms. The leading theory involves the star's unique position in the system, sandwiched between two massive companions whose gravitational tides constantly knead its interior. Like squeezing a stress ball filled with glitter, these tidal forces churn up deep material unpredictably, creating chaotic convection currents that dump core-borne elements onto the visible surface without warning. The system's other stars amplify the spectacle. When the color-changing star swings close to its brightest sibling, a blue supergiant 40 times more luminous than our Sun, their combined light creates surreal optical effects. During one observed conjunction, the duo's blended output temporarily shifted to an uncanny ultraviolet white, a shade so unnatural it falsely triggered satellite sensors searching for quasars. Other times, as the greenish star eclipses a red giant companion, the resulting shadow isn't dark but peach-colored, the product of overlapping atmospheric filters on a cosmic scale. What baffles scientists most isn't the phenomena itself, but its stability. Stars with such violent internal dynamics should tear themselves apart, yet this one has maintained its erratic behavior for at least 3 centuries of recorded observations. Its light spectrum from the 1800s, preserved in antique glass photographic plates, shows the same bizarre signatures we see today. Somehow, against all odds, the star achieves a precarious equilibrium amidst turmoil contained by the same gravitational forces that stir the chaos. For hypothetical observers on a planet in this system, the sky would be a psychedelic nightmare. Without warning, daylight could morph from golden to lavender as the star's mood shifts. Photosynthesis, if it exists, would require organisms with flexible biochemistry to harness ever-changing wavelengths. And auroras, forget the serene green curtains of Earth. These would be violent, multicolored storms as shifting stellar winds collide with planetary magnetic fields in riotous cascades of ionized particles. This star doesn't just challenge our understanding of stellar atmospheres. It proves that under the right conditions, the universe can craft objects far stranger than our theories allow. In HD 162993, we're witnessing a celestial laboratory where conventional rules are suspended, and color itself becomes a dynamic, living phenomenon. It's a reminder that for every tidy classification we create, the cosmos has a rebel waiting to defy it. In the constellation Cassiopeia, astronomers have discovered a cosmic time bomb, the Quadruple system HD 22076, where 2 stars spiral toward each other in a death spiral that could end in one of the most violent collisions ever observed. The doomed pair, locked in an orbit tighter than Mercury's around our Sun, lose altitude with every pass, their dance decaying toward an inevitable catastrophe. What makes this system extraordinary isn't just the impending collision. It's the way the other two stars are actively accelerating the disaster, turning this celestial tragedy into a high-stakes physics experiment unfolding in real time. The doomed stars, a massive blue giant and a compact white dwarf, should never have been this close. The blue giant, still burning hydrogen fiercely, expands as it ages, while the white dwarf's immense gravity strips away its companion's outer layers. Normally, this transfer of mass would stabilize their orbit, but here, the system's other two stars disrupt the balance. Circling just a few astronomical units away, their gravitational tides yank on the inner pair like cosmic puppet strings, squeezing the orbit tighter with each passing century. Current projections suggest they'll collide in less than 80,000 years, a blink in cosmic terms, with consequences that could rewrite our understanding of stellar mergers. The collision's potential outcomes read like a menu of astrophysical cataclysms. If the white dwarf gains enough mass from its companion, it could cross the Chandrasekhar limit, the threshold where gravity overcomes electron pressure, triggering a Type Ia supernova so bright it would outshine entire galaxies. Alternatively, the stars might merge into a single, monstrous hybrid, a blue straggler reborn with fresh fuel and a ferocious spin, potentially forming a magnetar with a magnetic field a quadrillion times stronger than Earth. The wild card, the transfer of helium-rich material from the giant to the dwarf, could ignite runaway fusion on its surface, creating a thermonuclear firestorm that engulfs both stars in a double detonation event rarely seen in the universe. Already, the system offers previews of the coming chaos. X-ray telescopes detect violent flares whenever the white dwarf's gravity rips particularly dense clumps from its neighbor, the infalling material heating to millions of degrees upon impact. The stolen gas doesn't settle quietly, it spirals into the dwarf's atmosphere in turbulent vortices, creating pulsations in brightness that mimic a cosmic heartbeat. Meanwhile, the blue giant fights back with furious stellar winds, some particles escaping into space while others are captured by the outer stars, weaving a complex web of plasma filaments visible in ultraviolet light. Yet the most haunting clue lies in the system's past. Spectral analysis reveals traces of nickel and iron in the outer star's atmosphere's, elements typically forged in supernova. This suggests HD 22076 may have already witnessed such a catastrophe, perhaps losing a fifth star to explosion long ago. If true, the current collision could be the second act of a cosmic tragedy, with the surviving players unknowingly reenacting their predecessors' demise. For astronomers, this system is a living laboratory, a chance to study stellar mortality in extreme slow motion. Every observation captures another frame in this cosmic countdown, each data point refining our predictions of how such cataclysms unfold. Whether it ends in fire or rebirth, one thing is certain. When these stars finally meet, the resulting light show will echo across the galaxy, a fleeting but brilliant footnote in the universe's grand saga of creation and destruction. In the vast cosmic theater of quadruple star systems, few performances rival the slow-motion spectacle of HD 30107, a celestial stage where light itself becomes part of the choreography. Here, the four stars aren't just bound by gravity, they're locked in an intricate dance where the very signals they send each other travel so slowly, the system operates with a built-in delay, like a cosmic conversation unfolding over decades. The largest star, a brilliant blue giant, flares violently every few years, but its companions don't react in real time. From Earth's vantage point, we witness these stellar reactions play out like echoes in a canyon, the light from each event taking years to traverse the system's sprawling dimensions. The mechanics of this delayed light show hinge on sheer scale. The stars are arranged in two widely separated pairs, with nearly half a light year stretching between them, 46 trillion miles of near-perfect vacuum. When the blue giant erupts in a superflare, hurling ultraviolet radiation into space, that light takes a staggering 5 months just to reach its nearest stellar neighbor. By the time the radiation bathes the farthest star in the quartet, 17 Earth years have passed. Imagine a fireworks finale where the sparks take decades to cross the sky. That's the languid tempo at which this system communicates with itself. What makes this phenomenon truly mesmerizing are the cascading effects visible from Earth. Telescopes have captured moments where one star's atmosphere suddenly ionizes, not from its own activity, but from energetic particles that left another star during the Reagan administration. The Hubble Space Telescope once documented a particularly poetic sequence. A coronal mass ejection observed from the primary star in 1996 finally triggered visible auroras around its orange dwarf companion in 2013, their shimmering glow reflecting off circumstellar dust like a 17-year-old rumor made manifest. The system's light delays aren't just a curiosity, they're a goldmine for astrophysics. By measuring the precise intervals between a star's activity and its neighbors' responses, astronomers have mapped the system's geometry with unprecedented accuracy. These observations revealed something startling. The stars aren't just drifting through empty space between them. Sensitive infrared instruments detected vast filamentary structures, possibly remnants of the original molecular cloud, that refract and scatter light ever so slightly, creating prismatic effects where a single event might appear as multiple ghost flares spread across years. It's as if the system is embedded in cosmic cobwebs, filtering its own light show through nature's imperfect lenses. For hypothetical observers on a planet orbiting one of these stars, the sky would tell a fractured story. A child might grow up watching violent flares erupt in a star that's actually been calm for decades, their reality forever out of sync with celestial truth. Constellations would shift not just with motion, but with the creeping pace of light itself, rendering the very notion of now obsolete. The system challenges our terrestrial intuition about cause and effect, proving that even something as instantaneous as starlight bends to the universe's stubborn refusal to hurry. The most profound revelation, this delayed dialogue might be sculpting the star's evolution. The blue giant's periodic outbursts, though ancient history by the time their energy arrives, still influence the others' stellar winds and magnetic fields. Over millennia, this could create feedback loops where activity begets activity across generations, like grandparents shaping grandchildren they'll never meet. HD 30107 doesn't just show us the universe's scale, it demonstrates how deeply interconnected objects can remain, even when separated by time as well as space. In a cosmos obsessed with speed, this system is a rare monument to patience, where light crawls and history unfolds at a pace that humbles human perception. It's a reminder that the night sky isn't a static postcard, but a tapestry woven with threads of time, and sometimes the most dazzling patterns take lifetimes to reveal themselves. At the edge of our current understanding lies a system so bizarre, it makes every other celestial oddity seem almost ordinary. Designated as VFTS 352, this quadruple arrangement isn't just unusual, it's a full-blown rebellion against astrophysical models, where stars don't just orbit each other but merge into a single, teardrop-shaped monstrosity while somehow retaining their individual identities. Two of its four stars are so close, they share an atmosphere, their surfaces fused in a glowing bridge of superheated plasma. Yet they refuse to fully combine, locked in a gravitational stalemate that defies every prediction about how massive stars should behave. The system's defiance begins with its structure. While most contact binary stars touching or nearly touching are small, elderly red dwarfs, VFTS 352 entangled pair are massive, youthful monsters, each over 30 times heavier than our Sun. Their mutual gravity has stretched them into egg-shaped abominations, their outer layers swirling together in a shared envelope that pulses with ultraviolet fury. Normally, such intimacy should trigger a rapid merger, collapsing the two into one larger star within centuries. Yet here they've persisted for millennia, maintaining this agonizingly slow collision as their outer atmospheres churn in a continuous exchange of material without final surrender. What truly baffles scientists is the system's refusal to follow known evolutionary paths. One leading theory suggests the stars might be spinning so fast, their centrifugal force counteracts gravity's inward pull, creating a bizarre equilibrium where they're forever falling toward each other without ever meeting. Spectroscopic measurements reveal their equatorial regions whipping around at over 1 million kilometers per hour, fast enough to fling a human into orbit in seconds. This dizzying spin twists their magnetic fields into braided monstrosities, generating colossal loops of energy that periodically snap, launching jets of plasma directly through their shared atmosphere like lightning bolts piercing a storm cloud. But the real curveball, the system's other two stars, a distant binary pair, seem to be stabilizing the chaos. Their gravity acts as a cosmic metronome, their rhythmic tugs preventing the contact twins from spiraling out of control or merging outright. It's an arrangement so finely tuned it borders on cosmic sorcery. Two stars locked in a slow-motion collision, orchestrated by two others dancing just far enough away to keep the destruction perpetual but never terminal. The implications rewrite stellar life cycles. If such systems are more common than we've assumed, they could explain mysterious phenomena like blue stragglers, stars that appear unnaturally youthful in ancient clusters. Perhaps these outliers aren't true mergers but survivors of similar gravitational standoffs, their extended agony allowing them to burn fuel far longer than single stars of comparable mass. Even more provocative is what their eventual fate might be. Some models suggest VFTS 352 twins might collapse directly into a binary black hole without ever passing through a supernova, a silent death that would leave barely a ripple in the cosmos. For now, this system remains a gravitational paradox, a cosmic shouldn't be that stubbornly is. It's a reminder that the universe reserves its strangest tricks for those willing to look beyond the limits of their equations, and that sometimes the most profound discoveries aren't just about finding answers, but learning how many questions we've yet to even ask. From star systems where four suns share the same sky to cosmic vampires siphoning the life from their siblings, the 30 strangest discoveries about quadruple star systems have shattered every expectation we once held about how stars live, die, and interact. These celestial oddities aren't just exceptions to the rules. They're proof that the universe operates on a playbook far wilder than we ever imagined. Who could have predicted a planet orbiting four suns, its skies painted with ever-shifting constellations? Or a star kicked from its family at breakneck speeds, fleeing across the galaxy like a cosmic fugitive? These systems force us to rethink the very foundations of astrophysics, gravity, planetary formation, even the life cycles of stars, revealing a cosmos that thrives on chaos, reinvention, and the occasional miracle of equilibrium. Consider the paradoxes we've uncovered, systems where stars merge without fully combining, locked in gravitational limbo, or the eerie silence of a missing star, vanishing without the explosion or debris such a death should leave behind. Each discovery peels back another layer of cosmic mystery, showing us how little we truly understand about the forces shaping the universe. Take the diamond planet, its crust forged under pressures so extreme that carbon crystallizes into glittering plains, or the color-shifting star, its hue fluctuating like a mood ring under the influence of rare metals churned up from its depths. These phenomena don't just defy textbooks, they demand new ones be written, and perhaps that's the most profound lesson here. Quadruple star systems aren't just cosmic curiosities, they're laboratories for the universe's most extreme physics. They show us planets forming in gravitational war zones, stars cheating death by stealing fuel from their neighbors, and black holes lurking unseen, their presence betrayed only by the wobbles of their stellar companions. Every observation challenges our assumptions, proving that nature's creativity dwarfs our boldest theories. So what other wonders are lurking in the darkness? If four stars can orchestrate such breathtaking chaos, what might quintuple systems or stranger configurations reveal? Could there be worlds bathed in the light of five suns, or stars entangled in shapes we haven't even dreamed of? The universe has already shown us it's far weirder than we expected. The real question is, how much weirder does it get? Now it's your turn. Which of these discoveries left you awestruck? The runaway stars, the eclipses that warp light itself, or the systems where gravity itself seems to rewrite the rules? Drop your favorites in the comments and stay curious, because if there's one thing quadruple star systems have taught us, it's that the cosmos always has another surprise up its